So, now let us get into the reconstruction part. Once we have formulated a procedure for signal decomposition, what it really boils down is the goal what we need next, right. I mean we have to understand what we need with this technique. So, I will give you two important applications. The first is for compression. We may want to identify the least energy components and null of the details that belong to that space, that is those WKs, K belonging to Z, you might figure out which of them are least energy components and null them off and get an approximate signal back, right. Let us say you are in some scale, say W2, and that energy was just probably 1% of the total energy, or you are in scale W3 that was just 0.1% of the total energy. That means you figure out where the energy is the least, null them off, because when you reconstruct it you would not have lost a lot of information. You would have lost some information. The information, I mean, if it has to be completely lossless, it has to be perfect transformation, right. I mean you transform it, you retain everything and then you get it back. And if you think that I want to compress my data, why do I need a lot of these signals in various subspaces, then you figure out where the components have the least energy in terms of what your threshold is in terms of energy threshold, null them off, and from there you reconstruct things back. You get an approximate signal, not what was original, but that way you will be able to represent the the signal post nulling with minimal number of bits or fewer number of bits. Okay, this is one idea, and this is done routinely in MPEG etc. MPEG 4 plus standards. I mean these days they are really very much evolved, but I mean MPEG 4 I think had wavelet transformations. The second application is denoising. We might want to identify spikes at a certain scale j and higher and notch out such spurious signals. So, basically after cleaning the signal basically after removing these spikes, post this, we can recover the signal. So, and there are plenty of applications from this purpose. I mean, we want to have a clean signal, we want to remove the noise first, get a clean signal to start with, and from which you can do many things. And I would also suggest that there are plenty of other applications such as in pattern recognition, etc., where wavelets can be used towards the feature extraction step. So, this is another possible application. You do a wavelet decomposition, let us say you got the coefficients in for f naught, you got the coefficients for w naught, w1, w2, w3, so on, right, and you can use those coefficients and in some form basically towards pattern recognition applications. So, if you have to recognize certain shapes, etc., you can do a decomposition, and the decomposition gives you certain features, and you might want to use those features in some way. So, wavelet can be in some cases a good tool for feature extraction. Okay. Now, let us formally begin the process of reconstruction. To obtain a reconstruction procedure, let us start with a signal of the form f of t is f naught of t plus summation I equals 0 to j minus 1 w I of t, where some w l belongs to the space capital W L. Now, here f naught of t is basically summation k belonging to the set of integers b k, I will use a different subscript here. So, I will call this as AK 0 phi of t minus k, and of course, this belongs to the space B 0. Now, W L of t is summa k belonging to the set of integers. This I will use B, BKL psi of 2 power L t minus k. This belongs to the space W L for 0 less than or equal to L less than or equal to j minus 1. Okay. We have these basics to start with. Now, what is our goal? Rewrite f of t in terms of phi of 2 power j t minus L, L belonging to the set of integers. right. This is our goal. So, we have all our f naught and WLs, from which we have to get this in this form, right. This is our reconstruction goal. Now, I will start with the procedure or some important steps. So, we should start with our, I call them friendly equations, and I call them friendly equations because we are seeing them over and over again. This is phi of 2 power j minus 1 t, which is basically phi of 2 power j times t plus phi of 2 power j times t minus 1, and then psi of 2 power j minus 1 t is phi of 2 power j t minus phi of 2 power j t minus 1. I mean, you just have to recall this carefully. Basically, this, if you think about, just draw this aside here. So, this picture should be very clear in your mind. So, if this is phi of x 1, this can be decomposed using phi of 2x plus its translate phi of 2x minus 1, right, which is phi of 2 times x minus half. That is, you have, this is the same as phi of 2 times x minus half, because if you have sketched phi of x, what you are doing is just translating this by half a time step here, right. So, this picture should be very, very clear in your mind, and your psi of x is basically this wavelet function, right. And where you take this and basically using this, you can, that is the reason why you have a negative sign. If you just get this picture in your mind, the rest will be very easy to go through that. So, I call them our friendly equations. So, maybe I will just call this equation number as d, just for consistency. So, phi of t is basically phi of 2t plus phi of 2t minus 1, I call it 1a, and psi of t is basically phi of 2t minus phi of 2t minus 1, I call it 1b, together this set is 1. Now, we have, by definition, f naught of t is basically in the linear span of phi of t minus k, right, which is basically some a k 0 phi of t minus k, and this I write it slightly in a different way. This is k belonging to z, a k 0 phi of 2t minus 2k plus summation k belonging to z, a k 0 phi of 2t minus 2k minus 1. Just I am using 1a here basically, and then what I am doing is going through the odd and the even parts. So, any shift k can be an odd shift and an even shift. So, using that I basically decompose this in this form. Okay. Now, I could call this as say equation 2a. Now, f naught of t is basically summation k belonging to z al, I just put a hat here for reconstruction, phi of 2t minus L, where this al hat belonging to scale 1 is a k 0 if L equals 2k. It is also a k 0 if L is 2k plus 1. This is the even case, this is the odd case. Okay. So, similarly, let us consider W naught of t. Let us denote this equation as 2b. Now, W naught of t equals summation k belonging to z BL of 1 psi, I could put a k here, some bk of 1 psi of t minus k, because it is the wavelet. Using the wavelet basis I can expand this, but I can write W naught of t as summation k belonging to the set of integers some BL hat of 1 phi of 2t minus L, because W naught belongs to V1, right. W naught belongs to V1. So, basically I have done two forms of expansion, one in this W naught space itself and other is in this space is using V1 as the basis. So, now BL hat of 1 is basically BK of 0 L equals to k and minus BK of 0 L equals 2k plus 1, right. I think this is what we land up with, right, because if it is even, this is BK 0, if it is odd it is minus. Now, if you sum, so let us designate this equation as 2c. Now, adding to b and to c, we get f naught of t plus W naught of t is summation L belonging to Z A L of 1 phi of 2 t minus L, where A L of 1 equals A k 0 plus B k 0 if L equals 2 k, and it is A k 0 minus B k 0 for L equals 2 k plus 1. This is basically equation 2D. Now, we can continue the process, that is steps 2A to 2D, starting with W1 of t, which is summation some k belonging to set of integers bk1 shy of 2t minus k, right, like W0 that we had earlier here. I think this has to be a 0 here, I think this is 0 here because scale 0 here instead of a 1 shy t minus k, and then this is basically bk1 shy because it's scale 1, okay, consistent with this. So, now we do this process 2A through 2D recursively, W1, W2, so on, right. So, how do we go about this? Now, let us see how this works. Now, you replace t by 2t minus k in equation 1, that is 1a and 1b that we started with. What we get is phi of 2t minus k is phi of 2 square t minus 2k plus phi of 2 square t minus 2k minus 1, and then we get psi of 2t minus k, which is phi of 2 square t minus 2k minus phi of 2 square t minus 2k minus 1. Let us call this equation 3, right. Just we are going to one scale down. Now, let us again consider f naught t plus w naught t plus w1 t. This should exist in scale j equals 2. So, therefore, we can write this within the linear span of the shift orthonormal basis in scale 2 using the scaling functions appropriately. Now, you take this function and therefore, you can now compare with the previous level like what we had. We can conclude that AL in scale 2 is basically AK in scale 1 plus BK in scale 1 for L equals 2K, and AK in scale 1 minus BK in scale 1 for L equals 2k plus 1. Okay, like what we had for the previous step from 2a to 2d, we just do this by adding f naught, w naught and w1 and then decomposing that and then linking it to a previous scale. Now, from the above, we are ready to obtain the reconstruction procedure and I mean this is for Haar wavelets. We are ready to obtain the reconstruction procedure and this can be summarized more formally, and I will state this as a theorem. Suppose f equals f naught plus w naught plus w1 dot 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 till wj minus 1 with f naught of t equals summa belonging to set of integers ak0 phi of t minus k belonging to v0 and wp of t, which is summa k belonging to the set of integers bk of p psi 2 power p t minus k belonging to the space wp for 0 less than or equal to p less than j. Then if this is true, then f of t can be written as L belonging to the set of integers AL of j in scale j phi of 2 power j t minus L belonging to the space Vj, where AL of p can be determined recursively. This is very important because we are linking one scale to another scale for p equals 1, 2, so on till j using the recursion AL of p equals AK p minus 1 plus b sub k p minus 1 for L equals 2k and a sub k p minus 1 minus b sub k p minus 1 for L odd, which is 2k plus 1 form. So, I think this basically, this is the statement of the theorem and the procedure that we derived is basically the proof of the theorem. Okay. So, I could have stated this theorem to start with and then intimidate you with a 2-page statement of the theorem here and continued with the proof, but I just gave you the feel for how the reconstruction procedure works and then stated the theorem towards the very end so that you can just connect the pieces together. Okay, I will give you a homework exercise here. Obtain the Haar decomposition for f of t equals 3 0 less than or equal to t less than 1/4 minus 1 between 1/4 and 3/8 2 between 3/8 to 5/8 and 0 between 5/8 and 1, obtain the signal after notching out any spike of 1/8 time units. Sketch the Fourier spectrum through all these scales. Okay, so you have a signal here, and perhaps for the signal any spike of 1/8 time step is a noise. So, null out this and then look at the frequency domain or the spectrum of the signal at each scale, and then analytically obtain what the reconstructed signal is, and in the frequency domain also interpret what your results are going to be. Okay. So, this completes the wavelet Haar wavelet decomposition as well as reconstruction. Now, we will in the next lecture interpret the wavelet decomposition and reconstruction within the framework of filter banks, and then you will see how filter bank theory is linked to wavelets. Okay, we will stop here.